All right, guys, today is lesson 9, and this is the first lesson of topic B. Today, our content goal is I can understand that a ratio table is a table of equivalent ratios. I can use ratio tables to solve problems. So today we'll be looking at a lot of ratio tables, which are going to look something like this at the top, this to that, and then you'll fill in numbers here. So let's go ahead and get started. All right, guys, so even though there is not a space for this in your classwork today, I believe it's important that you do write down this new term. So a new term that for topic B, I would find a space to either on your classwork notes, or maybe you want to write it on a blank paper and just insert it into your math folder. Or in your math binder, but just something we're going to keep coming back to is this idea of a ratio table. And the definition of a ratio table, it is a table in which all of the ratios are equivalent to one another. And I put down here, aka they have the same value. And you'll be seeing that modeled today. All right, so let's go ahead and start with example 1. And it says, to make paper mache, the art teacher mixes water and flour. For every 2 cups of water, she needs to mix in 3 cups of flour to make the paste. Find equivalent ratios for the ratio relationship 2 cups of water to 3 cups of flour. Represent the equivalent ratios in the table below. So before we do that, I want to talk about some quick questions to really help us be mindful of what we're thinking about here in this problem. So what does this ratio mean? For every 2 cups of water, there are 3 cups of flour. Well, that means that for every time we add 2 more cups of water, we're going to add 3 more cups of flour. Why is it worded for every 2 cups of water, there are 3 cups of flour? Well, it's worded by that because this suggests that we may be doing it repeatedly to make more than just the one batch. For example, in this problem, if the art teacher had a larger amount of students, this amount of paper mache wouldn't be enough, so she would have to increase the mix. Okay, and that answers the question, why would I do it more than once? Because yeah, if more students, you need a bigger quantity, so you would need to use that ratio in order to make more. All right, so now we're gonna go ahead and we're gonna complete the table. So we're talking about cups of water to cups of flour, and we are always gonna start with the ratio that uses the smallest whole numbers. So can I reduce 2 to 3? Is there an equivalent ratio that uses small whole numbers? Well, if I think about it as a value 2/3, that can't be reduced at all. So that's the smallest unit of whole numbers that I could start with. I mean, technically I could get like a fraction or a decimal to reduce it down, but we're not thinking about that yet in 6th grade. So let's go ahead and start. So again, for every 2 cups of water, there are 3 cups of flour for the mixture. So like I said, if for every time that we add 2 cups of water, we're going to add 3 cups of flour. So if I add 2 more cups of water, I would have 4 cups of water. 3 more cups of flour, I would have 6. Okay, if I add another 2 cups of water, I'll now have 6. If I add another 3 cups of flour, I'll now have 9. Okay, for every 2 cups of flour, so 2 more 8, I have 3 cups of flour, so 3 more 12, 2 more would be 10, and then 3 more would be 15. So there's our completed table. Now it wants us to find and notice the value of each of these. So just to demonstrate that to you, I'm going to add an extra column to my table where I find the value. So let me zoom in a little bit here. Okay, so if I have 2 to 3, my value is 2/3, and that can't be reduced. 4/6, that can be reduced. I could divide both sides by 2. And I'm going to get 2/15. 3 for the value. Sorry, that's not good. My best 30. Okay, 6 over 9. I can reduce that. I can divide both sides by 3. And I'm going to get 2 over 3. Well, what do you know? I'm starting to see a pattern here. 8 over 12. I could divide both sides by 4. And look at that. I get 2 over 3. 10 over 15. I bet you can predict what the value will be. I can divide both sides by 5. And I'm going to get 2 over 3 again. Okay, and this really connects with what we've been learning about the idea of equivalent ratios having the same value. But this is a great way to check your answers in the table, because if you're getting a different value in any of these places than you did the ratio table, you filled a number out incorrectly. Your quantity is off. So this is a great way to check your work. Prove that all of these ratios in my ratio table are in fact equivalent because they share the same value. All right, for example 2, Javier has a new job designing websites. He is paid at a rate of $700 for every 3 pages of web content that he builds. Create a ratio table to show the total amount of money Javier has earned in ratio to the number of pages he has built. Okay, so we're making a ratio table, which we have learned about. We saw it going vertically. Now we are seeing an example that a ratio table can also be horizontal, but it's the same idea, same practice. So I know for every $700, there are 3 web pages. Now, the first thing I want to kind of go to is recognizing where should I start? What number should I start with? So we just want to ask ourselves and double check, is there an equivalent ratio to 700 to 3 that uses smaller whole numbers? So if I were to look at it like this, 700 to 3, can this be reduced down at all? No, I can't reduce this down, because if I tried to divide 700 divided by 3, it wouldn't come out as an even number. So this is the lowest it can be reduced, so I'm going to start there. Now, it can be tempting to to just go quickly, not read the labels, and write 700 here and write 3 here. But that actually wouldn't be correct to how the table is set up. And let me zoom in to talk about that. So if I write 700, and let me get a pencil to show you. If I write 703, well, what I now say is that for every 700 pages, he will get $3. And that, first of all, would be a ridiculous amount of work for such a small amount of money, but that's also not what the table says. It says for every 700, for every 3 pages, he gets $700. So making sure that things are in the right place. Where I'm talking about the total money earned, I need to plug 700 in there. When I'm talking about the pages that are built, I need to put 3 there. Okay, so make sure you're always checking that the numbers correspond with the label in your ratio table. And we'll see that in another example in this lesson. But now I'm going to go ahead and fill out the table. So for every 3 pages, he gets $700. So if I add 3 more pages, that will be 6 pages. If I add $700 more dollars, I now have $1,400. Okay, again, and I'll just do one more and then I want you to complete it. So if I add another 3 pages, that would be 9. And if I add another $700 for those 3 pages, he now has $2,100. Okay, so go ahead and press pause to fill out the rest of this ratio table, and then press play when you're ready to compare your answers to mine. All right, so if I filled out the rest of my chart, as far as the pages go, it's counting. The pattern you should notice is that the pages, it's counting by 3 because he's making 3 pages, 3 more pages, 3 more pages to get that $700. So counting by threes up here, 3, 6, 9, 12, 15, 18, 21, 24. Okay, and then down here it's counting by 700 because again, that's the other part of the ratio. Every time he does 3 pages, $700 more dollars. 3 more pages, $700 more dollars. So 700, 1400, 2100, 2800, 3500, 4200, 4900, and 5600 is what you should have gotten. Down here, Javier is saving up to purchase a used car, and it costs $4,200. How many web pages will Javier need to build before he can pay for the car? So I do see that number 4,200 on my ratio table. So if he needs that $4,200, he's going to produce 18 web pages. So 18 web pages.